The Microsoft .NET Framework is a software framework for developing and executing applications on Windows client and server operating systems. It incorporates a wide range of technologies for implementing the complete gamut of applications required by most modern organizations, ranging from mobile solutions running on handheld devices and phones, through to desktop applications and web applications running across the internet, and onwards to comprehensive end-tier systems that can span multiple sites and traverse organizational boundaries. Underpinning the .NET Framework is the Common Language Runtime, or CLR, which provides the runtime environment for .NET Framework applications. The purpose of this presentation is to introduce the CLR, describing how it implements a robust, safe, and scalable environment for running Windows applications. The .NET Framework comprises three principal items. First, the CLR provides an abstraction layer over the operating system. It is responsible for running .NET Framework applications and provides them with controlled access to machine resources. Second, the .NET Framework class library contains a comprehensive set of types and functionality, making it easy to build applications that need to perform common actions, such as reading a file, displaying data on the screen, or arranging for tasks to be performed concurrently on separate threads. Finally, an ever-expanding set of development tools and frameworks is available for building increasingly sophisticated applications. This presentation concentrates on the first of these items. It describes the CLR from the perspective of a Java developer and compares its features and purpose to that of the Java Virtual Machine, or JVM. The purpose of the CLR is to provide a safe and secure environment for running .NET Framework applications. The CLR is responsible for locating and loading the various executable elements that comprise an application, managing the resources used by an application, protecting an application from other applications running at the same time, and preventing an application from attempting to perform operations that might impact the integrity of the computer or other applications running concurrently. Applications that are executed by using the CLR are referred to as managed applications. When you write a program by using C#, Visual Basic, or any of the other languages supported by the .NET Framework, the compiler converts your code into lower-level instructions in a language called the Microsoft Intermediate Language, or MSIL. MSIL is a pseudo-machine code that is independent of the architecture of the processor powering the computer. The MSIL code generated for a program is stored in a file called a module. Modules can be linked with resources and other modules to generate an assembly. An assembly can also reference classes and resources held in other assemblies. The main assembly for an application is typically compiled with the .exe file extension, and other assemblies holding utility classes are given the .dll file extension. When you start a .NET Framework application by invoking a .exe assembly, the CLR loads the assembly, reads the MSIL instructions from the assembly, compiles them into real machine instructions appropriate to the processor in the computer, and then runs them. If the assembly references other assemblies, they are also located by the CLR, compiled into machine instructions, and loaded into the process running the application. At first glance, the CLR appears to fulfill a similar role to the JVM that provides the Java runtime environment, and MSIL has many similarities to Java bytecode instructions. However, there are some philosophical and technological differences between the two environments. Microsoft developed the CLR as a mechanism to support programming language independence and interoperability. You can write .NET Framework applications by using any language that has a compiler that generates the appropriate assembly format and MSIL instructions. Additionally, an application can reference code in other assemblies, and these assemblies do not all have to be written by using the same language. For example, a C# class can invoke a method in a Visual Basic class without requiring any form of translation because the C# and Visual Basic compilers both generate the same MSIL code. The CLR was primarily intended to run under Windows, although Microsoft have released a shared source version that can run under Unix. In contrast, the original purpose of the JVM was to provide a platform for a single language, Java, that could run on almost any platform. The same Java application can run on any operating system that provides a JVM, and the results should be the same. Language interoperability was not originally a major concern. However, many vendors and other organizations have since started producing compilers that generate Java bytecode instructions for other languages, so this distinction between the CLR and the JVM has become a little blurred. Furthermore, some commonly used scripting languages, such as Python and Ruby, have implementations that can run under the CLR and the JVM, enabling code written in these languages to execute in both environments. A CLR assembly is similar to a Java jar file in that it provides the organizational structure for a set of compiled classes. An assembly wraps the MSIL code for the classes and contains a manifest listing the classes that it holds. The manifest also lists any dependencies that the assembly has on classes in other assemblies so that they can be loaded by the CLR. The CLR implements assembly versioning. When you compile a set of classes into an assembly, you can provide version information which is stored as part of the metadata for the assembly. When you reference another assembly in an application, you can specify which version of the assembly to use, and the CLR will locate and load the correct version at runtime. This versioning mechanism enables you to deploy several versions of the same assembly on the same computer for use by different applications without causing any version conflicts. The process of resolving an assembly referenced by the CLR is known as binding. The binding process only requires that the CLR understands how to find the required assemblies and does not depend on any Windows registry settings. Deploying a .NET Framework application is therefore often just a matter of copying the assembly files that comprise the application to a folder on the computer, a technique known as Xcopy deployment. The CLR follows a well-defined algorithm for locating assemblies. The simplest scheme involves implementing an application as a set of one or more private assemblies. In this scheme, the .dll assemblies referenced by the application are stored in the same folder as the .exe assembly. If an assembly is not found in this folder, the CLR can look in subfolders that have the same name as the assembly. Assemblies can also be located on other network computers and downloaded as required by an application. Additionally, you can configure a search path for an application to locate assemblies by using an application configuration file. Application configuration files will be described in more detail later. Although this mechanism sounds more complex than the simple class path scheme implemented by the JVM, it is more suited to resolving references to different versions of an assembly at runtime. Private assemblies are useful for self-contained applications, but if several applications reference the same .dll assembly, you can end up with multiple copies of the assembly file installed in different locations on your computer. To combat this, the .NET Framework also enables you to build shared assemblies and deploy them to an area known as the Global Assembly Cache, or GAC. The GAC is a set of folders managed by the .NET Framework that provides a central repository of assemblies for the computer. When you build a shared assembly, you can use the tools provided with the .NET Framework to deploy the assembly to the GAC, and applications can then reference this assembly from the GAC. To ensure the veracity and authenticity of shared assemblies held in the GAC, they must be signed with a private key. Applications that reference these assemblies are provided with the public key necessary to decrypt this signature. If the CLR cannot decrypt the signature of an assembly by using the public key held by an application, then the assembly is treated as suspect and is not loaded. I mentioned earlier that compilers that target the .NET Framework generate MSIL code, and the CLR is responsible for compiling MSIL instructions into machine code at runtime. You can also handcraft MSIL code, and the .NET Framework SDK provides the MSIL assembly utility, ILASM, for generating an assembly from a file containing MSIL instructions. The MSIL code in an assembly is portable across machines running the Windows operating system, but the compiled machine code generated by the CLR is processor dependent. I also mentioned earlier that an application can reference assemblies that reside on network shares and other remote locations. The CLR is responsible for downloading these assemblies and resolving these references at runtime. However, to ensure the integrity of the code in an assembly and prevent damaging bugs that could lead to corruption caused by a malformed or malicious assembly, the CLR performs a verification pass prior to compiling the MSIL instructions into machine code. For example, all code is examined for type safety, and each method call is examined to ensure that the correct number and types of parameters are provided and that any return value is used properly. By default, and to save time, only assemblies loaded from remote locations are subject to verification. Assemblies located on the same computer as the application are considered to be sound, although the code that they contain may be subjected to various security checks described later. In common with many JVM implementations, verification and compilation of a .NET Framework assembly occurs on a just-in-time basis by the CLR. The compiled code is then saved in memory by the CLR so that if the same code runs again later as part of the same application, it does not need to be recompiled or verified. An administrator may elect to precompile assemblies that are held in the GAC by using the native image generator utility nggen. The CLR can then use these precompiled images at runtime. This can help to improve performance in some situations, but nggen code might not be as well optimized as that which is JIT compiled, because the nggen utility cannot make the same assumptions about the way in which the code is invoked and run that the JIT compiler can. When you start a .NET Framework application running, you actually create a process that hosts the CLR, and the CLR then takes over responsibility for loading the various application assemblies and running the code. This is similar to the way in which the JVM runs a Java application, except that you do not explicitly have to invoke the CLR from the command line in the same way that you do the JVM. In both cases, each application executes in a separate process. This strategy helps to isolate applications from each other, and one job of the operating system is to ensure that a process cannot accidentally or maliciously access the memory used by another. This separation comes at a price, however, and if two processes running on the same computer need to communicate with each other, they need to perform potentially expensive cross-process calls involving marshalling and unmarshalling data as it traverses process boundaries. This is not normally a major concern for .NET Framework or Java applications running on the desktop, but can lead to performance and scalability issues in a server environment where multiple concurrent applications may need to share resources. To counter the expense of traversing process boundaries, the CLR implements application domains. An application domain, or app domain, is an environment for executing a .NET Framework application that is created in the host process that runs the CLR. A single process can host multiple app domains, and each app domain can run different .NET Framework applications. The verification mechanism implemented by the CLR helps to ensure that two .NET Framework applications do not adversely interfere with each other when they run in different app domains in the same process. But the fact that they run in the same process means that they can communicate with each other more efficiently and share resources. For example, if two applications running in different app domains in the same process reference the same assembly, the CLR only needs to load that assembly once. App domains provide a major benefit to server-side application hosts, such as web servers. A server process can create, destroy, or recycle app domains dynamically as requests from client applications arrive, and isolate the processing for each client request in its own app domain. A single server process can handle many client requests in a safe and controlled manner, and this architecture helps to improve scalability. The Java Application Isolation APR, defined in JSR 121, describes a similar mechanism for the JVM, enabling Java applications to share resources, although to date this feature has not been widely implemented. A common technique employed by many applications that predate the CLR, as well as Java frameworks such as Spring, is to store configuration information in a separate file. This data might include information such as the location of a database to connect to, or the folder location for saving and retrieving data used by the application. The idea is to avoid hard coding such details, so that an administrator can update this information as necessary without requiring that the application is rebuilt. The CLR adopted this idea and automatically looks for a configuration file named after the application with the .config suffix every time it starts running a desktop application. The .NET Framework provides a number of its own configuration settings that can be included, such as whether to log performance data and where, what form of authentication to use to identify users, where to find local assemblies required by the application, and so on. A developer can also include custom configuration data in this file. The configuration data is held in an XML format, and an administrator can easily modify this file by using a text editor. Visual Studio also provides tools and XML schemas that can help to validate configuration data and assist in this task. Additionally, the .NET Framework implements computer-wide configuration settings in a file called machine.config stored in the Windows system folders. When an application starts running, the CLR first retrieves settings from the machine.config file and then applies any settings from the application-specific configuration file. These application-specific settings may override those in the machine.config file. In this way, an administrator can define global settings for all applications in a single place and customize them on an as-needed basis for individual applications. Web applications and services are configured in a similar manner. They can have a local configuration file called web.config deployed with the application, while global settings are held in another system-wide web.config file stored in the Windows system folders. With the JVM, the logical organization of the source code for an application mirrors the physical structure of the compiled code. For example, the source code for a Java class must be stored in a file with a name that reflects the name of that class. Java organizes classes into packages, where a package represents the physical organization of the set of compiled class files. A package corresponds to a folder, either in a jar file or on disk, and the JVM locates packages based on the value of the class path variable defined by the host environment. The strong association of the compiled code with the physical organization of that code can cause problems if, for example, a developer needs to move files to a different source code folder or wishes to rename a class or a file. Such changes can cause compile time and runtime exceptions caused by the JVM being no longer able to locate a class or package, and such errors can sometimes be difficult to resolve. The CLR follows a different approach. The file names and physical organization of the source code for a .NET Framework application does not have to reflect the structure of the compiled code. Remember that in the .NET Framework, classes are compiled into assemblies, and the metadata for an assembly provides a list of the classes that the assembly contains. The CLR uses the search algorithm explained earlier to locate assemblies and resolve references that an assembly may make to other assemblies. At the logical level, in the .NET Framework, you can group types into namespaces. Like a Java package, the purpose of a namespace is to help organize related types together, and to help avoid clashes between types that happen to have the same name but are developed by different programmers. All types in the .NET Framework are qualified with the namespace to which they belong. Namespaces can also be nested, so a namespace can contain child namespaces. Assemblies are simply a physical deployment feature, while namespaces provide the logical organization of types within assemblies. It is important to understand that there is a many-to-many relationship between assemblies and namespaces. A single assembly can contain types defined in many namespaces, and a single namespace can be implemented by types spread across many assemblies. This is an extensibility feature. You can easily add new types to an existing namespace by creating a new assembly containing these types and specifying that they are part of this namespace. To make the type available in an application, you simply add a reference to the specific assembly that holds the type to the application. The object models implemented by the JVM and the CLR are similar. They both provide single inheritance with a single root type called object. In both environments, you can define interfaces, and a class can implement as many interfaces as it needs. However, the CLR takes built-in support for object orientation to a higher level than that provided by the JVM. For example, the CLR enables you to define properties as first-class members of a type, and they are not simply naming patterns that are interpreted by a programming framework. This strategy helps to reinforce encapsulation in a much stricter manner. In the same way, the .NET Framework defines events as fundamental types that are handled natively by the CLR rather than depending on an event handling framework layered on top of the runtime, as is the case with the JVM. To support events, the CLR provides delegates, which are references to methods and that can be used to invoke a method indirectly. In a .NET Framework application, you can subscribe to an event by creating a delegate that references a method to run when the event occurs, and then add the delegate to the event. When the event is raised, the delegated method runs. Both Java and the .NET Framework implement generics. Java currently supports generic types at the language level. They are implemented purely by the Java compiler, and as of Java 6, the JVM has no built-in knowledge of generic types. Consequently, there are limitations concerning their functionality. Additionally, Java only currently supports reference types as type parameters. You cannot use int as a type parameter, for example. Some of these issues may be addressed in Java 8. In contrast, in the .NET Framework, generics are supported by MSIL instructions and are handled by the CLR. This enables the CLR to perform more robust type checking than is currently the case with Java, enabling a wider range of use. For example, a .NET Framework generic class can access the type parameters used to define the data types that underpin the class, while the type erasure mechanism of Java renders such code illegal. Furthermore, a .NET Framework generic class can take any valid type as its type parameter, including value types. As with the JVM, the CLR provides support for structured exception handling in your application code. Methods can throw exceptions if they detect an exceptional situation, and calling methods can catch these exceptions or allow them to propagate. In the CLR, an unhandled exception that propagates all the way out of an application into the app domain trips a default exception handler that terminates the application after reporting the exception to the user. The .NET Framework class library includes a large number of exception types, many of which have an equivalent in the Java class library. As with Java, the CLR enables you to define your own custom exception types. You can inherit from the application exception class to do this. Like the JVM, the CLR maintains application memory as a managed heap. The CLR has its own multi-generational garbage collector which can detect and tidy up memory used by deallocated objects and return it to the heap. The CLR will also periodically compact the heap to try and prevent fragmentation from occurring. By default, the CLR itself determines the most appropriate time to perform garbage collection, but in contrast with the JVM, the .NET Framework also enables classes to implement a more deterministic approach that you can use not only to free up memory, but also to release other resources acquired by an object. To apply this approach, you implement the iDisposable interface in a class and write a dispose method that frees the resources. The C# and Visual Basic programming languages provide the using construct that automatically invokes the dispose method of a disposable object when it goes out of scope. In CLR parlance, classes are referred to as reference types, and they behave in a very similar manner to Java classes. They are passed by reference as method parameters and return types, so any changes you make to the data in an object persists when the method completes. The CLR also supports value types. They are created and destroyed automatically as they come in and out of scope. They are not subject to garbage collection in the same way as reference types. Value types are so called because they are passed by value as method parameters. Any changes made are not reflected in the original data item passed in, and these changes are lost when the method completes. In this respect, value types in the CLR behave in a similar manner to the primitive types in Java, such as int, boolean, float, char, and so on. However, in the CLR, value types are structured. They can contain fields and define methods and properties, and are more akin to the struct types found in C and C++. In fact, the built-in types of C# are simply aliases for a set of structs provided in the .NET Framework class library. For example, the int type in C# is actually an alias for the system.int32 struct. At first glance, therefore, a Java developer might be tempted to equate an int in C# with the java.lang.integer object, but bear in mind that the C# int type is a value type, but a java.lang.integer object is always passed by reference. In a similar vein, enumerated types, or enums in the CLR, are value types, whereas enums in Java are reference types. As well as being able to define your own types and classes, like Java, the .NET Framework provides an extensive class library, providing a broad range of functionality that an application can use to interact with the operating system and perform common tasks such as writing to a file, displaying a window on the screen, or reading user input. The .NET Framework class library comprises a number of assemblies deployed to the GAC and is organized into a set of namespaces. Much of the core functionality required by most applications is located in the system namespace. You can think of this namespace as being analogous to the java.lang package in the Java world. Other namespaces contain more specific features. For example, the system.collections namespace implements a set of collection classes, and the system.windows namespace and its various sub-namespaces, such as system.windows.controls and system.windows.media, provide the classes required by applications that implement a graphical user interface. This diagram shows some of the more commonly used namespaces and their approximate mappings to the equivalent packages in the Java class library. You should notice that the functionality of the .NET Framework class library exceeds that of the core Java class library and includes elements that require Java Enterprise Edition or third-party packages such as JBoss JPBM to provide the equivalent features for Java. The .NET Framework class library contains a large number of namespaces and types spread across a range of assemblies. However, not all of these types are applicable to every kind of application. For example, many of the namespaces contain types designed for use by server applications. To reduce the footprint and improve the deployment time of applications that don't necessarily require all of this functionality, the .NET Framework defines a streamlined subset of the .NET Framework class library containing the elements most commonly needed by desktop and client applications, but with the server functionality stripped out. This subset of the .NET Framework class library is called the .NET Framework Client Profile. Consequently, when you deploy a desktop or client application that references the client profile to a computer, only the assemblies that implement this subset of the .NET Framework class library have to be present on that computer. Application security concerns controlling access to the resources that an application can request on the host machine, and is a fundamentally important consideration both of Java and .NET Framework applications. At the application level, both the JVM and the CLR follow similar models. By default, desktop applications and applications executed from the command line run without restriction and have full access to the computer, although the operating system itself may enforce limitations depending on the identity of the user running the application. In the Windows operating system, this is true both for .NET Framework applications and Java applications. If you need to limit the operations that an application is permitted to perform, such as preventing it from sending or receiving net requests for example, you can configure the appropriate software restriction policy at the operating system level, or use the App Locker utility if you are running Windows 7 or Windows Server 2008 R2. These policies are managed by Windows and are completely transparent to the CLR and the JVM. A standalone application running on a user's desktop can implement additional restrictions by loading a security manager. The security manager intercepts requests to access resources and evaluates them based on the sensitivity of the resources and the code that is requesting access, granting or denying the request as appropriate. Both the .NET Framework and the Java class library provide default security manager implementations, and you can extend these classes if you need to implement a custom security scheme. It's worth emphasizing that in the .NET Framework and Java, the decision of whether or not to use a security manager is made by the application or the way in which it is configured and is not enforced by the operating system. For example, in the .NET Framework, an application can load and run assemblies by using an app domain object, which in turn provides a security manager functionality. Hosted applications, such as those running in IIS for .NET Framework applications or a Java application server, and client applications running in a hosted environment such as a web browser, execute in a sandbox which limits the operations available. As with a standalone application, the sandbox is implemented by using a configurable security manager, except that this time it is loaded by the host environment. In the .NET Framework, the host environment typically creates an app domain for running each application, and the app domain provides a security manager functionality acting as the sandbox. All requests to access resources made by hosted applications are subject to scrutiny by the security manager. The security manager typically implements a configurable policy that is intended to prevent an application from opening the system up to an external attack, such as opening network ports, surreptitiously sending and receiving requests from an external site, and reading and writing files in the local file system. In the .NET Framework, the decision of whether or not to grant access to a resource is based on evidence provided by the host environment concerning the origin of the assemblies comprising the application. For example, an assembly downloaded from a location across the Internet is usually less trusted than an assembly installed on the same computer as the host environment. You may also need to restrict access to operations and resources based on the identity of the user running the application. The CLR implements role-based security, or RBS, to help achieve this. Authentication is handled by the host environment outside of the CLR. The .NET Framework implements a provider model, enabling an administrator to plug in any suitable authentication and authorization provider. The CLR can be configured to specify which form of authentication the host should employ, and RBS works in conjunction with most common authentication mechanisms. This is similar to the architecture typically implemented by enterprise Java solutions, which employ the Java Authentication and Authorization Service to provide an interface to the local authentication system. Using RBS, you can annotate methods with attributes that specify any roles that the authenticated user must have in order to run those methods. The CLR performs the authorization when the application invokes these methods. These attributes are similar to the Java security annotations available in Java EE5 and those described in JSR 250, available with implementations of Java SE6 and onwards. For a finer grain of control, the .NET Framework class library provides a set of low-level APIs in the system.security namespace and child namespaces that a developer can employ to verify the identity of an authenticated user and programmatically allow or deny access to various resources as defined by the logic of the application. These APIs are analogous to those provided in the Java.security package with the JVM. When Java first appeared, most computers had a single processor. Although it appeared sometime after Java, the same was true for the .NET Framework. Both Java and the .NET Framework recognized that even in a uniprocessor environment, it was still useful to implement multi-threading. Originally, the JVM implemented threading either by acting as a wrapper to the threading library provided by the operating system if it supported threads, or by acting as its own thread scheduler if the operating system did not support threads. The CLR had an advantage in this situation. Being targeted at a single operating system, namely Windows, it could always assume that the underlying platform provided threads, so it didn't need to implement them itself. Consequently, the threading model available to applications running in the CLR is actually just a thin veneer over native Windows threads. The .NET Framework class library implements the thread class in a system.threading namespace which acts as a wrapper around Windows threads, and most of the thread synchronization features available to native Windows applications is made available to .NET Framework applications through other managed types in a system.threading namespace. As technology has advanced, many desktop computers now contain multiple processors or processors with multiple cores, and they are now capable of performing true multitasking. The most recent version of the .NET Framework has extended the multi-threading capabilities provided with the .NET Framework class library to take advantage of such processors with the Task Parallel Library, or TPL. This library has been available for a couple of years now and contains types that provide an abstraction for a set of concurrent tasks, including how to schedule and synchronize them. Using the TPL, you can build applications that will run in a simulated concurrent manner on a single processor with a single core, but can automatically adjust themselves to perform real concurrency if more processors or cores are available. You don't need to amend any code. All an application developer has to do is to define the operations that can be performed in parallel and run them by using tasks. The TPL takes care of creating the appropriate threads, dynamically optimizing them according to the number of processes available in the current workload of the computer, and then allocating tasks to these threads. Many developers building server-side applications for the .NET Framework have found the TPL an invaluable addition for ensuring that their code remains scalable as more powerful computers with increasing number of processors become available. The proposed fork-join framework, mooted for Java 7, is expected to provide similar functionality to the TPL. Hopefully, you should now understand that the purpose of the CLR is to provide a controlled and safe environment for running applications, and it achieves part of this promise by taking charge of the memory and resources that an application uses. However, you may need to integrate components and other elements into your applications that are not designed to run in such an environment. For example, you may need to integrate unmanaged code developed by third parties into your solutions, or you may have a number of items developed by using other technologies such as COM. Two key elements of the .NET Framework and the CLR that can help in this respect are the Platform Invoke service, commonly referred to as pinvoke, and COM interop. pinvoke provides a generalized mechanism to load code from an unmanaged library into a managed process, and then call functions in this library from managed space. It's similar in concept to the Java native interface implemented by the JVM. When you invoke unmanaged code from a .NET Framework application, it runs in the same process as managed code, although it has its own unmanaged heap and unmanaged stack, referred to collectively as unmanaged space. pinvoke transfers parameters and return values between the two spaces by using the interop marshaller. However, the CLR cannot verify that the code in an unmanaged DLL is well behaved. Therefore, it's vital that any unmanaged code that you execute from the CLR is trustworthy and functions correctly. pinvoke differs significantly from the JNI in its implementation. You can specify a function that pinvoke makes available to managed code by defining a method stub that's tagged with the DLL import attribute. This attribute indicates which library pinvoke must load and the name of the function in that library to call. When a managed application calls this method stub, pinvoke loads the unmanaged library and runs the specified function. This process is transparent to the managed code. Integration with the COM component involves a few steps. First, a developer uses a tool called TLB-imp provided with the .NET Framework to generate an interop assembly. The interop assembly contains the metadata that lists the interfaces and classes exposed by the COM component. At runtime, the CLR uses this interop assembly to generate an intelligent proxy, referred to as a runtime callable wrapper or RCW. The managed application calls the RCW, which in turn takes care of handling the necessary interactions with the COM subsystem to instantiate the component and manage its lifetime. This process is also transparent to the managed code. Dynamic languages, such as Python and Ruby, are being increasingly used by many organizations. These languages incorporate runtime type checking rather than the static compile time verification originally implemented by the CLR. Version 4 of the .NET Framework has added the ability to support versions of these languages that target the .NET Framework, IronPython and IronRuby being the most established examples, through an extension known as the Dynamic Language Runtime, or DLR. The DLR enables managed code written in a language such as C# to directly instantiate a dynamic object and invoke its methods without requiring the developer to create and manage any form of proxy or intermediate code. The DLR is not tied to a specific set of languages, but instead implements an extensible architecture through pluggable language binders. A language binder provides the logic necessary for the DLR to invoke a method in a specific dynamic environment, and how to marshal and unmarshal data between the environment provided by that language and the .NET Framework. The binder can also perform a limited amount of runtime type checking if necessary. The .NET Framework 4 provides binders for several languages, including IronPython, IronRuby, JavaScript, and even the .NET Framework itself. It also includes a binder for COM, enabling you to use the DLR as an alternative to COM interop for interacting with COM components exposed by tools such as Microsoft Office. It's interesting to note that the JVM is also moving in a similar direction, with support for integration with dynamic languages due to appear as part of Java 7. In this presentation, I gave you an overview of the CLR, comparing and contrasting its features with those of the JVM. Both environments provide similar features, although the CLR is optimized for applications running under Windows. The scalability features of the CLR, the protection it affords for applications, and the security support that it provides make it an ideal platform for developing and hosting a wide range of solutions, from single-user applications running on a mobile device through computationally complex graphical applications running on a desktop to high-volume, high-throughput applications running on an enterprise server.